Okay, we are at section 27.3, Kirchhoff's rules. And let's share the screen. And they start off with what looks like a simple circuit, but the fact that they throw in a battery between A and B changes this from a series parallel circuit, which it would have been without the battery, to a more complicated circuit. And so we need rules for handling these types of more complicated circuits. And that's where Kirchhoff's rules come in. There's two rules for Kirchhoff's rules. The junction rule. At any junction, the sum of the currents must equal zero. Let's go back. And so A here, that's a junction. B, that's a junction. This little black dot where the I2 is going down, that's a junction. The little black dot where the negative battery of this 18 volts is, that's a junction. So these are junctions. And so it says that at any junction, the sum of the circuits must equal zero. Well, if a current is going into a junction, it's positive. If a current is leaving a junction, it's negative. Basically, what it's saying is as much current goes in, that much current has to be going out at the other branches of the junction. So that's rule number one. Rule number two is the sum of the potential differences across all elements around any closed circuit loop must be zero. In other words, if you start at the positive end of a battery and start adding the voltages, some of the voltages are going to be negative, you'll get back to zero. We'll look at that in more detail. Let's first look at the junction rule. At any junction, the sum must be zero. So the total amount of charge flowing in the branches on the right must equal the amount flowing in the single branch on the left, and they equate it to water in a dividing branch there. So here I1 would be positive, and I2 and I3 would be negative. So basically what it's saying is I1 plus I2 plus I3 is going to equal zero. Well, if I2 and I3 are negative, that will be the case. So I1 minus I2 minus I3 is equal to zero. I2 and I3 are negative because they're leaving the junction. Okay, so that's the junction rule. The loop rule, the sum of the potential differences across all elements around any closed circuit loop must be zero. And they showed you this before. As you exit at point B, it's positive. As you exit point D and point F, it's negative. So you end up with the same thing. You end up with zero at the end. So let's look at, in each diagram, delta V equals VB minus VA, and the circuit element is transverse from A to B, left to right. So we go left to right. So charges, basically what I'm doing is reading from page 724 of chapter 27. It's the section that goes along with this graphic. Charges moving from the high potential end of a resistor toward the low potential end. Charges move from the high potential end of a resistor toward the low potential end. So if a resistor is traversed in the direction of the current, the potential difference, delta V, across the resistor is minus IR. So that's figure A. If a resistor is traversed in the direction opposite the current, the potential difference, delta V, across the resistor is plus IR. That's B in the figure in the PowerPoint. Now let's look at some batteries. If a source of EMF assumed to have zero internal resistance is traversed in the direction of the EMF from negative to positive, the potential difference, delta V, is plus E. It's just the voltage of the battery. If a source of EMF assumed to have zero internal resistance is traversed in the opposite direction, the direction opposite the EMF, from positive to negative, the potential difference, delta V, is minus E. Now, let's look at an alternative view. Let me stop this share and share my iPad. Oh, do I even have my pen? I do. Good thing. Okay, let's look at this circuit here. Now, if we follow this path, whenever you see the direction of the current, you put a drop of plus and minus, plus and minus. Now, let's follow this loop. Coming out of the battery, as you exit, as you go in a loop, and we're going to take a loop going around this way, all right? This is our loop in this direction. This is our loop. Now, let's go ahead and erase that so it doesn't get too cluttered. Now, you see I put a plus and a minus on the R1 and the R2. Now, let's exit the battery. We have a plus delta V, and as we exit, so we've exited this way. Whatever you exit, you take that sign. So we've exited the battery. That's a plus. Now we're exiting the resistor. We're going to take the sign as we exit. So it's a minus I times R1. And as we continue along, we're going to exit R2. As we exit R2, we're going to take its sign, it's minus, and it's I R2. Remember, the same current all throughout. And then we come back around this way. So with the plus delta V and the minus IR1 and the minus IR2, that should equal to 0. Okay, now let's look at a little different circuit. Let's as we look at the current, we put a plus here and a minus here, a plus here and a minus here. Now let's, any of these paths that we take, there's actually 3 possible loops that we can look at here. We can look at this loop, that's 1. We can look at this loop, that's 2. We can look at this loop, that's 3. So there's 3 possibilities. I tend to go clockwise. You can do it counterclockwise, but you just have to pay attention to the exiting device. We'll do one to show. Let's take the outer loop, this big one over here. So as we exit the battery, it's a plus delta V, and we continue on. As we exit R1, it's a, notice the minus, you remember as we exit the device, it's a minus I1 R1. And as we come back around, there is more components, so that has to equal 0. That's 1. Now let's look at it. Let's just look at this bottom loop around here. So as we exit the battery, that's plus delta V. And as we go around this way, it's a minus I2 R2. That has to equal 0. Now let's clear this out. And let's do this. Let's do this loop here, this inner loop. Now let's start here, and we're exiting R2, so that's I2, it's plus I2 R2. Now we're making our loop go around this way. Come on, I messed that up. We're making our loop go around this way. Now we're exiting R1, that's a negative, so it's going to be minus I1 R2, and that's going to be equal to 0. So I like to think of it that way. As you exit, you pay attention to the currents, and you use the sign as you exit the device. Now, on some of these complicated the circuits, you may not know which way the current goes. Well, you just assume a direction and you write your equations, and it should come out. You'll end up with a negative current, which means you assume the wrong direction, and you just make up for it in the when you come up with the solution. All right, so let's go back and let's stop this share and go back to the PowerPoint. And there's some problem-solving strategies. And again, I'm going to do some reading. Again, this is at the bottom of page 724, problem-solving strategies of Kirchhoff's rules. The first one is conceptualize. Study the circuit diagram and make sure you recognize all elements in the circuit. Identify the polarity of each battery and try to imagine the direction in which the current would exist in the batteries. Remember, try to imagine the current. If you're wrong, if you just assume it, and if you're wrong, you'll end up with a negative current, and you just compensate for that in your calculation. Number two is categorize. Determine whether the circuit can be reduced by means of combining series and parallel resistors. Sometimes you can. If so, use the techniques of section 27.2. If not, apply Kirchhoff's rules according to the analyze step below. So let's go to the analyze step. Assign labels to all known quantities and symbols to all unknown quantities. So assign labels to known quantities, symbols to unknown quantities. If you must assign directions to the current in each part of the circuit, you must assign directions to the currents in each part of the circuit. Although the assignment of current direction is arbitrary, you must adhere rigorously to the direction you assign when you apply Kirchhoff's rules. Apply the junction rule to all junctions in the circuit except one. Now apply the loop rule to as many loops in the circuit as are needed to obtain the combination of the equations from the junction rule. As many equations as there are unknowns. And we're going to be solving simultaneous equations. To apply this rule, you must choose a direction in which to travel around the loop, either clockwise or counterclockwise, and correctly identify the change in potential as you cross each element. Be careful with signs. Follow the rules in figure 2712, or remember the exiting rule as you take the sign as you exit for the current that you've assumed. Solve the equations simultaneously for the unknown quantities. And then finalize. Check your numerical answers for consistency. Do not be alarmed if any of the resulting currents have a negative value. That's what I was saying. That only means you have guessed the direction of the current incorrectly, but its magnitude will be correct. And I think that with that we'll stop there, and then the next section will go to RC circuits.